Hey, hi guys, this is Hemant and today we are going to solve a Leetcode daily challenge. So as the problem says, it's maximum swap. You are given a integer num, and you can swap at most two digits. Sorry, you can swap, yeah, two digits at most once and you can get the maximum valued number. So okay, they'll be given a number and you can swap any two digits only once and see if you can make it max value. If you can't do it, then you can just return the num as it is. What do you mean by that? You can see in the first example it's 2736. If I can just swap 7 and 2, now it's bigger number. This can be the max value by swapping two digits. And you can see here no swaps required because it's already max. What do you mean by no swaps required? In sense, if the number has a digits in a decreasing format, then there is no point in swapping because it's already max. So let's just see the constraints. So constraints are 10 power 8, which is really huge. And let's just see the topic also. Since they are saying math and greedy, we can actually solve this in multiple ways. Okay, so what is a brute force? Extreme brute force. Whenever you see this thing, right, you need to maximize it. If you go with the digit numerics theory, how to max the value? I need to max the starting indices, the place, ith place. So for 2, I'll try and find the maximum element on the right side. Okay, if at all there exists, and then I'll swap and I'll get the max value. Now if let's just say there is a number here itself, not 2 but 8, so there is no huge number to swap it with 736 because 8 is greater than all 736. So we come to here and then again we'll find the max element if there exists, and again here and then again here. So this is an n squared solution. Why n squared solution? At the worst case, if all the digits are 99, you have to traverse throughout the digits and see if there is existing any max element on the right side. So that's the one thing. And how to actually optimize it. See, in the brute force itself, what you are actually trying to do is for every digit you're trying to find the right max element, right? What if I say that instead of finding every time, what if I pre-compute it and use it, right? I can use prefix digits. What do I mean by prefix digits is, you see here 7 7 6 and 6. See, I'll traverse from the back. For 6 maximum is 6, 6 and 3 6, 6 and 7 7, 7 and 2 7. So for every digit I found the right most max element. Now again I need to traverse these digits and see if at the very first place if I can swap, then I'll swap and I'll return. If not, again I'll see for the next elements, and then this is the thing we can actually do. But again, this will take a space of number of digits, and then also you need to traverse two times. So since they have given the topics math and greedy, we are going to solve in math and greedy itself. Again, the reason why I told these two approaches is, with the first approach, now you know how to come up with second approach. Instead of finding every time right max, we pre-compute and use it. Now using the second approach, we can come to the math greedy. How? See, you found for every element the right max, right? Now what if I say, instead of pre-computing it, I will see if whenever I find the right max element, I will store its index, and while traversing back, if I see some element smaller, then I know that I can swap it. But I don't want to swap it earlier. I want to see throughout the end, because for me this position is not important, this position is more important. So I'll traverse the whole point, whole back, from the left side to right side, sorry, from right side to left side, and I'll find where and all I can actually swap these elements. In the end we'll swap the elements and then we can get the max. I know, we will try run this example and you will understand it. So initially max element itself is 6, Okay, and what its max that elements index, max elements index is 3. Now I'll come here. Okay, I'll come at 3 element. I'll see if, okay, is 3 greater than max element? No, of course it's not. Then I have no idea whether I can swap or not, but I'll just store its indexes. So what is the max element index? 3, and current element index is 2. So see, this is simply saying that we have a chance by swapping this, we might get a max value, but we are entirely not sure because we need to traverse the whole point. So that's the thing. So that is the case, and max element here it's not updated because 3 is not greater than 6. And we'll come at here. See, once we come at here, 7 is actually greater than 6. Okay, so I will update my max to 7, and also max elements index. Keeping track of this is also very important because I need to swap max element itself, right, for the left elements. So that's the thing. Now this is done. Okay, I did this thing, and then we'll come at 2. See, 2 is not greater than max, right? So what I can do, I can update my current max index, which is 1, and current element which I'm at the 2, which is 0. See, at the end of point I got these both indexes. I just swap these indexes and I can get the answer, right? See, this is the greedy approach which they were trying to, show us. This will actually work because I was actually trying different way, and even see, you can see I made wrong submissions. So yeah, without a further ado, let's just implement it, and with code I think you'll get even better clarity. So initially I can't just swap. I was saying array, right? I will just clear it here because see, you cannot manipulate in num and swap all those things. So instead we'll convert it into array, character array. Why character array? It's because since these are all digits, if I subtract with ASCII of 0, I can get the actual integer value of the particular character. So that's the whole point. So in Java, we can just do this. We can convert any integer to string, and then I can convert to array. We can get the length. So we have the length, and we need this particular max element index and all these variables. So initially int max element, let's just say it is the last element itself. So that is array at n-1, and you need to do it with ASCII value because since we are using characters, if you subtract with ASCII of 0, you'll get the integer representation of that particular number. And also int max initial index is itself n-1. Now we have the two indexes, which is this for swapping the two elements. Now what you can do is, in the end, you need to swap these particular things and you need to return the answer, right? Yeah. So first we'll follow through our logic. What we were trying to do is, we'll traverse the whole array from the back, in leaving the last element because already we used that element. So we are going to traverse from here. So that is n-2 -0. So what we were trying to do, if at all, okay, if at all current element minus ASCII, if it's actually greater than max element, right, that means this is a new max element. I need to update this is the max element with this, and also I need to update max index as well, which is the I itself. If not, what I need to do, I need to store these two indexes, right? Because these two indexes. So when I need to store, if at all that element was actually less than, okay, in this case I need to store it. So index 1 at max index, and index 2 is current elements index. So once this is done, and there is an edge case, and what is that edge case? If let's just say you actually never found, okay, in this particular example you will never found index 2. Index 1 will always be found, because you see index 1 will always be stored with max index, and if at all you're traversing from back, if you're not getting that small element, because see, if it is already sorted, there is no element. If 3 is not less than 7, again 7 is not less than, sorry, 3 is not greater than 7, again 7 is not greater than 9, so you'll never find smaller. So this condition actually never executes, in that meaning that you will never find index 2. And let's just make this as index 1 with, instead of initializing it -1, we already know the max index. Let's just do this thing. So if now I can only swap if index 2 is not equals to -1. That means there is some element. Now by swapping this, actually I can get the max value. So what I can do, I can take array at index 1, this is a basic swap, not that big of a deal. So yeah, we swapped. Now we need in the answer, we need to represent it. In the end we are going to return the answer. So how are we going to construct the answer? We are going to traverse all the elements in the air. Oh, sorry, I've actually used this thing, right? So how I'm going to construct the answer multiplied by 10, this is a basic math, and then array at I, subtracting with ASCII value. So yeah, this is pretty much it. We discussed the edge case. Okay, I think we discussed the edge cases. Let me just run and see if it works for all test cases or not. Yeah, okay, let me just submit and see. So as you can see, it beats 100% 0 milliseconds, because instead of every time, see what the reason why it's extremely fast, because the reason every time, instead of converting a character into integer and then integer into character, instead of that I was using ASCII values. Using ASCII values is pretty fast. So I think we solved it with math and greedy, because see, every time we are trying to find a max element, for every max element on the left side, if there is a small element, then we greedily storing these indices, hoping that this might help. By swapping this I can get the max value, but I'm not entirely sure. So that's the one way to do it. And regarding time complexity, we are only traversing, regarding time complexity, we are only traversing the whole digits once, and then actually we are doing it actually twice, because we need to construct the answer as well. See, instead of this particular thing, if I did this, right, integer dot parsing new string of array, even this will work. It's just an inbuilt functions. Okay, let me just submit and see. Yeah, it will work. I just want to see if it's actually faster or somewhat slow. So here it's maybe because of the way they designed the test cases, it's showing very fast, but in the actual way, if you do this one, right, this is actually pretty faster than this whole using inbuilt functions. So yeah, That is pretty much it. And space complexity, we are only using few variables. We are traversing 2 times, so linear space complexity. I hope you understood the approach, greedy approach with the dry run and the implementational as well. Yeah, see you in the next video.